Welcome to today's paper reading. Today's paper is titled, Diffusion Prior-Based Amortized Variational Inference for Noisy Inverse Problems. This paper was published on AR14 by Sojin Lee and colleagues from Korea University. The abstract highlights recent advancements in solving inverse problems using diffusion models as priors. However, these methods are computationally intensive and lack scalability. To overcome these issues, the authors propose a novel approach called diffusion prior-based amortized variational inference, DAVI. This method enables single-step posterior sampling and improves generalization across unseen samples. Extensive experiments demonstrate DAVI's superior performance in image restoration tasks, and the code is publicly available. Noisy inverse problems are prevalent in various fields such as image restoration, medical imaging, and astronomy. These problems typically involve estimating the original data from noisy observations using a forward model. However, due to the opposed nature of these problems, accurate estimation is challenging. Diffusion models have shown significant success in various generation tasks, inspiring their use in solving inverse problems. Recent methods have utilized diffusion models as priors, but they often require iterative sampling and struggle with generalization. To address these issues, we introduced diffusion prior-based amortized variational inference, DAVI, which enables efficient single-step posterior sampling and improved generalization. Figure 1 presents the representative results of diffusion prior-based amortized variational inference, DAVI. The top row illustrates a qualitative comparison between our method and existing baselines. The bottom two rows highlight that DAVI delivers robust solutions with fine-grained details across diverse image restoration tasks, all achieved through a single evaluation of a neural network. In the context of inverse problems, several studies have utilized diffusion models. DDRM, for instance, employs singular value decomposition in the spectral domain. However, this approach can be computationally expensive. DDNM and PyGDM introduce pseudo-inverse guidance without SVD, but they struggle with noisy measurements. DPS approximates the time-dependent likelihood using Tweedy's formula. FPS connects Bayesian posterior sampling with Bayesian filtering. RedDiff explores the variational perspective in pixel space. Unlike these methods, our approach aims for efficiency by solving the inverse problem in a single step. Additionally, our work adopts amortized variational inference, AVI, which uses a neural network to represent the variational distribution family, offering a more efficient and scalable solution compared to traditional variational inference methods. The forward stochastic differential equation, SD, for the diffusion process is given by dx equals ftxt dt plus gt dw, where ft is the drift coefficient and gt is the diffusion coefficient. The reverse SD, used to transition from the prior distribution to the data distribution, is defined as dx equals ftxt minus g2t nabla xt log p, xt, dt plus gt dw, where nabla xt log p, xt, is the score function and w is the reverse time Wiener process. The score function is approximated by a neural network S theta, xt, t, which is optimized using a denoising score matching objective with a time-dependent weighting function lambda, t. Figure 2 illustrates the optimization procedure of our proposed diffusion prior-based amortized variational inference, DAVI. The figure shows how our method alternates between optimizing the score function S psi and the neural network I to minimize the Kullback-Leibler KL divergence between the implicit posterior distribution Q, x0, y, and the true posterior distribution P, x0, y. The true posterior distribution is approximated by the likelihood P, y, x0, and the diffusion prior S theta. This optimization enables efficient single-step posterior sampling for both seen and unseen measurements, enhancing the generalization capabilities of our method. The diffusion prior-based amortized variational inference, DAVI, framework is designed to tackle inverse problems by using a pre-trained diffusion model as a prior. This framework learns a neural network that directly maps a measurement y to the posterior distribution p, x0, y, of the clean data x0. This allows for efficient posterior sampling and zero-shot inference. The training objectives focus on minimizing the KL divergence between the implicit distribution and the true posterior, incorporating data consistency loss and integral KL divergence to ensure stable and optimal results. Additionally, the perturbed posterior bridge (PPB) is introduced to enhance the generalization power of the method by providing intermediary measurements during training. Figure 3 illustrates the process of integral KL divergence (IKL) in the context of diffusion prior-based amortized variational inference (DAVI). The IKL loss perturbs the implicit distribution into a smoother distribution using the forward stochastic differential equation (SD) to address the disjoint support problem. This is visualized at two time points, T1 and T2, where T1, T2. The gradient of the IKL loss, nabla-Likl, updates the parameters of the implicit distribution in a direction that minimizes the discrepancy S psi, theta between the score functions S psi and S theta. This process ultimately aims to minimize the discrepancy between the implicit posterior distribution Q, x0, y, and the true posterior distribution P, x0. The figure demonstrates how this optimization enhances the convergence robustness of the KL divergence, particularly in scenarios where the supports of the two distributions are misaligned. Figure 4 illustrates the perturbed posterior bridge (PPB) concept. Panel A displays the sampling distributions of parameter A. Panels B and C show the PPB between two 1D samples, specifically x equals 0 and y equals 1, under different perturbation schedules denoted as sigma. The perturbation is plotted along the y-axis, highlighting the deviation from a linear bridge between y and x. This figure aids in understanding how varying perturbation schedules affect the PPB, which is crucial for the effective training of the neural network I in the diffusion prior-based amortized variational inference (DAVI) framework. In this slide, we discuss the experimental setup for evaluating DAVI against state-of-the-art methods. We compared DAVI with DDRM, DDNM+, DPS, PyGDM, DiffPIR, and RedDiff on the FFHQ and ImageNet datasets at a resolution of 256 by 256. The tasks include Gaussian deblurring, 4x super resolution, and box-in painting. For evaluation, we use PSNR to assess measurement fidelity, LPIPS to measure structural fidelity, and FID to evaluate image realism. The implementation details involve using a pre-trained diffusion model, setting P, A, as a beta distribution, and sigma A as a monotonically increasing function. Figure 5 presents a qualitative comparison of our DAVI model against various baseline methods, selected based on their performance metrics. The results clearly indicate that DAVI excels in producing vivid and realistic images while preserving intricate details of the measurements. For instance, in the second row, methods like DDRM, DPS, and RedDiff blur the microphone, whereas DAVI maintains its clarity. Similarly, in the first and third rows, DPS and DiffPIR fail to capture small details like eyes or green spots on the sock and crow, respectively. In contrast, DAVI not only generates realistic images but also ensures consistency with the original measurements. This qualitative analysis aligns with the quantitative results, highlighting DAVI's superior performance in both realism and detail preservation. Table 1 presents comparative results for solving noisy inverse problems, specifically focusing on Gaussian deblur, 4x super resolution, and box-in painting tasks on the FFHQ 256 by 256 dataset. The table highlights the performance metrics including peak signal-to-noise ratio, PSNR, learned perceptual image patch similarity, LPIPS, and freshet inception distance, FID. The results indicate that the proposed method DAVI significantly outperforms other state-of-the-art methods in terms of FID and LPIPS scores, demonstrating its superior performance in image restoration tasks. Table 2 presents comparative results for three noisy inverse problems: Gaussian deblur, 4x super resolution, and box-in painting with a centered 128 by 128 mask on the ImageNet 256 by 256 dataset. The table highlights the highest performance in bold and the second highest performance underlined. Key metrics include NFI, number of function evaluations, PSNR, peak signal-to-noise ratio, LPIPS, learned perceptual image patch similarity, and FID, freshet inception distance. DAVI hours demonstrates competitive performance across all tasks, particularly excelling in the Gaussian de Blur and 4x super-resolution tasks. This table underscores DAVI's effectiveness in handling inverse problems with high consistency and realism. Table 3 presents the robustness of various methods to the unknown noise scale sigma y in Gaussian deblurring tasks on ImageNet 256 by 256. DAVI, our method, demonstrates superior performance without requiring the noise scale, achieving a PSNR of 23.47, pips of 0.347, and FID of 63.37. In contrast, methods like DDRM and PyGDM, which require the noise scale sigma y, show significant performance degradation, with DDRM having a PSNR of 16.09, pips of 0.595, and FID of 157.38, and PyGDM with a PSNR of 21.80, pips of 0.446, and FID of 82.98. This highlights DAVI's effectiveness in handling inverse problems without prior knowledge of the noise scale, maintaining consistency and realism. Table 4 presents the inference speed in seconds per image for 4x super-resolution tasks on the FFHQ 256 by 256 dataset, measured on a single Titan RTX GPU. The table highlights the highest performance in bold and the second best in underline. It compares various methods including DAVI, DDRM, DDNM+, DPS, PyGDM, DiffPIR, and RedDiff, showing their respective times and FID scores. This data is crucial for evaluating the efficiency of different super-resolution techniques in practical applications. Table 5 presents the results of an ablation study conducted on the Gaussian deblurring task using the FFHQ dataset. The study investigates the contributions of integral KL divergence, IKL, and perturbed posterior bridge, PBB, to the DAVI framework. Configuration B, which includes IKL, shows a significant improvement in the FID score by 13.08 points compared to Configuration A, highlighting the effectiveness of IKL. The study also evaluates the role of PBB, demonstrating that introducing perturbations in Configuration D improves both LPIPS and FID scores. Notably, Configuration F, which incorporates a monotonically increasing schedule for the perturbation scale, achieves the most superior performance with an FID improvement of 17.49 points compared to Configuration D, underscoring the importance of the perturbation schedule and sampling distribution for optimizing the implicit distribution. In this paper, the authors introduced the Diffusion prior-based Amortized Variational Inference (DAVI) framework, which is designed to address noisy inverse problems through amortized variational inference. This framework optimizes an implicit distribution parameterized by a neural network, aiming to minimize the KL divergence between this implicit distribution and the true posterior. This optimization enables efficient single-step posterior sampling without the need for measurement-wise optimization. Additionally, the authors propose a novel perturbed posterior bridge, PPB, to enhance the generalizability of the implicit distribution. Extensive experiments conducted on image restoration tasks demonstrate that DAVI outperforms previous state-of-the-art diffusion-based methods. However, the use of human datasets in this work raises ethical concerns, particularly regarding the potential for restored images to resemble real individuals. The authors acknowledge these concerns and emphasize the importance of ethical mindfulness and the development of robust strategies to address such potential issues. Thank you for watching.